Welcome back to ECE 320A. Your second homework problem set is due on Tuesday. After the weekend, it's due. There is a practice exam for exam number 1 that's posted on D2L. There's 2 versions of that exam. One does not have the answers with it, and if you want to sort of check to see how well you're doing, you could try to solve that, but you do have the solutions available to check your work after the fact. I'm introducing some special office hours for Tuesday morning, since the homework problem set is due on Tuesday instead of a typical maybe Thursday. If you have last-minute questions that you would like to have addressed, I will try to be in office hours from 9 until 11 on Tuesday morning. That's the 7th of February. Are you interested in having a review for exam number 1? If that's the case, I have a couple of time slots that I want you to vote on, and maybe I should just, I don't know how accurately I can count live in class, but maybe we'll just have a show of hands in a little bit. So be thinking when you would like to have it. It will be held in ECE 530. That may be a little tight, but I think we'll be able to fit most of you in. Maybe we'll have to bring some blankets and sit on the floor. I never remember exactly how many seats are in ECE 530. It's a little shy of 50, and I think there's 50 plus of you here, but I'm guessing 1 or 2 of you might oversleep the 5 o'clock start time. But if you all are there, I think we're still okay. But I want you to vote on whether it's Tuesday or Wednesday. The exam will be the following, or a week from today, actually. And we won't have the review until after your homework set is due. I know you won't be worrying about the exam probably until after you've turned in the homework assignment. The homework or the exam review is post homework number 2 submission time, which is 4 o'clock on Tuesday afternoon. What I want to cover today then is now listed. First, we'll vote for our exam review date, either Tuesday or Wednesday, and that will be at 5 o'clock in room ECE 530. I know that I can get that room. I don't know if it's too crowded and too confusing, we'll look for a different room subsequent to exam number 1, but we won't that particular time. Today what I want to do is get into the 3-phase circuit discussion relative to the Y-Y interconnection structure. We'll look at the diagram, we'll look and see what happens with the current in the neutral conductor. We'll examine conditions for the circuit to be balanced. That means all 3 phases are singing together properly. Then, if we are in a 3-phase balanced circuit, we can actually extract from that a single-phase equivalent and simply analyze everything in one single phase. And if somebody asks us for something in the B phase or the C phase, and we've analyzed the A phase, since it's balanced, we know how to translate that. We know the relationship between the angles. If we have a balanced system, how are the angles separated from each other? If it's a positive phase sequence and the A phase is at 0 degrees, where is the B phase? Minus 120. And if the A phase was at 20 degrees, the B phase would be a minus 120 from that, and it would be at minus 100. Is that okay? Then we will start talking about the difference or distinguishing between line-to-line voltages, which a lot of times are just called line voltage, and the line-to-neutral. In a YY configuration, the line-to-neutral voltage is different from the line-to-line voltage, and we'll try to make that clear. That's in a Y-configured source. There's a distinction between the A phase voltage and the A line-to-line voltage, and we'll try to make that clear in today's lecture. Let's begin with a vote. And you're either voting for red or blue. I apologize if you want to vote for red and that's not your favorite color, but hopefully red and blue are school colors and you're not partial to either one of those. How many are interested in a Tuesday evening? Oh, this is going to be equal, isn't it? So how many are in the first row? Can the first row count? How many are in the second row? Keep your hands up high. Third row, fourth row, and fifth row. Now we need to add those up. First row, how many hands were raised? I think there's 8. How many are in the second row? Do I see 4? How about the third row? 1, 2, 3, 4, 5. Fourth row? 1, 2, 3, 4, 5. And the fifth row? 1, 2, 3, 4. So how many is that? I see 10 plus 16, 26. Is that right? Wow, that's about half of the enrollment. Let's see if we're all in attendance today. How about the red Wednesday? First row, 1, 2, 3. Second row, I can be selective maybe in my vision to throw the vote. Third row, 1, 2, 3. Fourth row, 1. Fifth row, there's somebody has 3 arms. 1, 2, 3. I think I see 5, so that's 15. And all the others. What I will try to do is I will try to record that session and post it on D2L. So if you can't attend, you get some sleep aid on Tuesday evening and Wednesday if you watch it. Is that okay? All right, we'll have it on Tuesday. All right. So we'll have our review session for Exam 1, and those of you who voted for Wednesday, you are allowed to come on Tuesday if it works into your schedule. That's fine. That is allowed. You're all allowed to attend. I won't hold you to your vote, unlike maybe the presidential election. Pardon? Oh, if I get... Wow, that's an idea, huh? This is more confusing than primary elections. All right. Now that I have you participating in random conversation, let's talk about the YY three-phase circuit and what that looks like. Let's see if I can sketch that on this small screen. This will be the generator side or the source side, and let me call the top one. And now this is a Y, but it's spread out so it looks like a T on its side. But if you bend those top 2 over, you could maybe make it look more like a Y. But this I'm going to call A prime. Here's B prime, and there's C prime. And the bar above that means it's a phasor quantity. And probably, well, you'll just have to determine whether or not it is representing an RMS value or not. And that node between them I've actually labeled as N, and that will be our reference node designated in a minute. Then we have, associated with each generator, we have the internal impedance of that generator, which we're just lumping into or labeling Z sub GA for the A phase. B phase is similarly, shouldn't have done that. So this is those three leads would be the leads coming out of our generator. The A phase, the B phase, and the C phase, and internal to that are these impedances, which will be the generator impedances, a resistor in series with an inductor. Then we have our line behavior, which I will call Z sub LA, Z sub LB, and Z sub LC. That's the impedance of the transmission line. And then at the load side, we have our A phase impedance, Z sub A, our B phase impedance, and those are supposed to be capital letters to distinguish those. There's the C, B, and A terminals of our load. And it is possible in a YY configuration to identify a neutral conductor. This physically could exist. And I will connect that between these, and let me call the impedance of that neutral conductor Z naught. There's our load section. Here's our line section. And here's our generator or source side. Questions on that configuration? And as I said before, this node, little n, it will be our reference node. We'll reference all our polarities to that particular location, little n. That is our YY three-phase connected system. And you might note, so this is a Y, or you could say that in terms of the low or the source side, it looks like a tipped over T, and on the generator side, it looks like that, and then you put it through a mirror and it looks just the opposite on the load side. But hopefully you can see how you can bend or contort that Y into what we have created in the diagram. And I am trying to be consistent with this double subscripted notation, in that the voltage drop is from the first subscript to the second. Meaning on the generator side, V sub A prime N is the drop between the A prime node and the N node, the reference node. That's the significance of that. And we could actually label some of these quantities other than just the voltages in this diagram. We could have a current flowing in the neutral conductor. Suppose we'll call that I sub 0. In the A phase, we could be going from little a to big A. And in the B phase, our current is, so our phase currents or line currents will be flowing from the source to the load in orientation. That's how we will define the positive sense of those currents. Question? So now what we want to do, the question concerns the current in I sub 0. And that's the first quiz that I want to give you. I want you to determine, or actually let's see if we can determine by writing KCL, so you can thank your classmate after class for that question or that quiz. But at this little n, can you write, or please write KCL at little n? In terms of the source voltages and these impedances that are introduced in this diagram. You should have then an equation involving VA prime n, VB prime n, VC prime n, and all of these different impedances. I want you to write KCL, so that's the in-class participation or the quiz. The ICP is write a KCL equation at node n, and you can assume that it's not necessarily a balanced system to write that equation. Little n, so the question is, what's the voltage at little n? That's our reference node. That will be basically our 0. You can, well, here, why don't we say, just so that we don't get all confused, why don't we just call this voltage right here from that node, capital N, all the way over to the reference node. We'll just call that capital V sub n. We'll leave off the little n. But you could put it on there if you wanted. I think that's what your question was. This node is now at a potential V sub capital N, and that will be a phasor. Meaning if you had a voltmeter, you would attach the negative lead at little n, and you would now be tapping these different locations to measure the voltage at A prime, B prime, and C prime, and at capital N to obtain those voltages that are labeled. And once you have those voltages, use those in your equation for KCL at node lowercase n. Yes? Can we not use those currents? You can use the currents, but if you use the currents, I want you to rewrite those in terms of the voltages and the impedances. Question? Yes, KCL at little n. So if you write KCL, write it with respect to little n. All right, since I have a plane to catch after class to get to Indianapolis before Sunday, no, I'm not. I am catching a plane, but I'm going in the opposite direction. I can't spend too much time waiting for you, but I wanted you to start to think, what in the world is going on here? So what will happen if we write a KCL at little n? In terms of the currents, which is what somebody suggested, we have this I naught coming into the node and all the other I's going out or leaving. Meaning on an exam, if all else failed, you could at least write KCL in terms of those four currents that you've identified in each of those four lines. And that would give you maybe a half a point out of 100 possible, but at least you would get a half a point. But here, that's now the defining relationship for the currents. Is everybody comfortable with that? The way we labeled it, we had the neutral current coming into the node and all of the other source currents or generator currents leaving. Now what we need to do is rewrite each of those currents in terms of the voltages that exist in the circuit. Let's look at the neutral conductor. We have Vn on the right, and that's the voltage dropped only across Z0 in the neutral conductor. And that's our current flowing through the neutral conductors. Everybody see that? V0 over Z0, or Z sub 0. I0 is then this V0, or V sub n, I should say, over Z sub 0. Now let's look at what I sub AA is. And that's a lowercase a, capital A. It's not two double subscripted A's. We're not in Alcoholics Anonymous. You might be after analyzing this circuit, but we won't be. So we want to find I sub AA here. How do we do it? It's the we have the impedance. We have three impedances in series. We can just add those in the A phase. And now we simply find the voltage dropped across those three impedances, and that's simply V sub A prime little n minus V sub capital N. That's the voltage dropped across those three impedances in the A phase. And that will give us I sub AA as we've labeled I sub AA. This is then V sub A prime N minus V sub N all over Z sub GA plus Z sub LA plus Z sub A. And now you simply need to put that in the photocopy machine and copy it and change the A's to B's and the A's to C's. And we're done. Question? Yes, the voltage at little n, that's our reference node. The question was, what's the voltage at little n? And we're assuming that's our reference node, and in all of our analysis, we find one common node in the circuit and say, that's my reference, and label everything relative to that. And in this case, it's a little foreign because it's hanging up there on the left middle location. It's not down at the bottom of our circuit, which is where we always sketch it. But it now, you can just say, that's my reference, that's 0, and I'm going to refer everything to that little n spot, that node. Question? I'm not sure I'm understanding the question, but here I want I sub AA bar. I want to find that current. Well, that's the current that would flow from left to right if the polarity at A prime was higher than the polarity at V sub n bar. And the polarity at A prime is defined to be V sub A prime n. Is that making any sense? So look at V sub A prime n as this tall tower. That's at a high potential, and V sub capital N a little lower. That's the potential drop between those, and now you have that impedance between them that you're dividing by to get your current. Question? We just use V sub A prime N minus V sub little n, which is 0, and just divide that by the sum of all the impedances there. I'm not sure I even see what you're asking, but yes, we could. We could define everything relative, or try to find I sub A, but we have to remember that sort of, well, the way we're going to be viewing it is that neutral conductor is going to be sharing all three phases neutral current. That's the way to sort of view it. And you could think of that neutral conductor as having like three separate signals going through it, the A phase, the B phase, and the C, and we're dumping them all into that conductor. And for that reason, let's just keep everything a little cleaner by referencing that voltage on the far right, and then we don't muddle things up with Z0. But you'll see where that could come into play when we start analyzing it. But for now, are you okay with this parameterization of I sub AA? We can now write V sub BB the same way, structurally. That's now our KCL equation that we were hoping to write based on the in-class participation quiz. That's what I was anticipating or looking for. That's one way of structurally writing that. You have your currents in the three different phases that are supplied by your sources, and you have your neutral conductor current that really is the sum of all three of those. Now that we have that, let's go a little bit aside and start seeing, because the way it's written right now, we haven't said anything about the relationship between Z sub GA, Z sub GB, and Z sub GC. Those could be different. We haven't stated that they're the same. But in a balanced configuration, we want all of these different impedances of the three different phases to be identical to each other. Let's now state conditions, and then we'll see what that implies relative to what's happening in the neutral conductor. Let's look at this definition, or what we will refer to when we say a three-phase circuit is balanced if, one, we have V sub A prime N, V sub B prime N, and V sub C prime N, forming a balanced three-phase set of voltages. So those source or generator voltages form a set of balanced three-phase voltages. Two, I want my generator impedances to all be the same. For the three-phase circuit to be balanced, I also need my line impedances to all be equal. The A phase, the B phase, and the C phase. And finally, as you can anticipate, I want all of my loads in the three different phases to be equal. Now, question. Yes, so you could collapse 2, 3, and 4. The question was, can't you just look at the total impedance in each line and say that's equal? And yes, that's true. This just keeps the three distinct impedance locations separate. And it says, well, if you're building a generator, hopefully all three phases look the same. And if that's the case, then if you build a line that's servicing that load, hopefully all three lines look the same. And all your loads then have to be the same to make that true. And so you hopefully will sort of see these three subparts naturally existing or occurring in your system. Question? So it's the question, will you have a balanced system if the sum of these three impedances in each phase are equal? Then you can, but it's really to be, let's say, true to this definition, let's just assume all three of the separate parts are equal. That our generators look the same, our lines look the same, and our loads look the same, and that's going to give us a balanced system. That's the cleaner way to think about it. Question? So you want 3 times the current going through Z naught. That's correct. You want Well, you want, if you go back, you have all three of these currents, I sub AA, I sub BB, and I sub CC, all flowing into capital N, and that's going to then drive the neutral conductor current. But now let's look at what happens. If indeed we have this condition in place, that we have a three-phase circuit that's balanced, if all four of these conditions are true, if our voltages form a balanced three-phase set, that's going to give us something. And what that gives us is the following fact. The fact that that allows us to state is that if the system is balanced, that voltage on the right is exactly the same as our reference voltage. It's 0. Capital V sub capital N is the same as capital V sub little n. It's at the same polarity. I'm sorry, it's at the same potential. This isn't a math class, but let's see where that comes from. We'll sort of sketch a proof, an engineering proof of that. So here's what people were wanting to do, and so we'll please them. Let's just say that our impedances, we will sum those all up and call those our phase impedance, Z sub phi. Now we don't have to write that all the time. That sum of those three impedances. That's our load impedance, our line impedance, and our generator impedance. If that's the case, our KCL equation, let's now combine all of the capital, or the V sub capital N pieces on the left. So all of those minuses, we add those V sub n's to both sides, and they're going to fly over to the left, and that will just give us the A prime, B prime, and C prime upstairs on the right. Meaning, we now have on the left V sub n times 1 over Z sub 0 plus those three pieces from each of the different phases. And on the right, the denominator is the same in all three. That's the Z sub phi. And upstairs we have, or in the numerator, we have our three generator voltages. But what did we show last time that equals if those are balanced? That's 0. Remember, if we added those head to tail, head to tail, head to tail, those phasors sum up to 0. And on the right, we now have 0 over Z sub phi. Or capital V sub little n bar, I'm sorry, capital V sub capital N bar times some quantity, which that's actually non-zero. Those impedances are giving us something, and that's non-zero. So we can divide by that non-zero number and show that V sub n is indeed 0. Now there's a couple of ways to use that information. Now that we know in our circuit diagram, now that we know that the potential at little n and capital N is the same, that provides us with a couple of options. We can either completely remove that Z naught, or we can just replace it with a short circuit. Since those 2 points are at the same potential, it really doesn't matter. And that's what we're going to use to our advantage to simplify the analysis. In a balanced 3-phase circuit, we can either pull off that neutral conductor completely, or we can replace it with a bare wire or a pure wire, no resistance. Those are our 2 cases that result when capital V sub n is the same as V sub little n. And that's what I want to write now. If V sub capital N is 0, then we'll have a couple of possibilities. We'll call them star and double star. There is no voltage that's dropped between the source neutral, which is lowercase n, that's our reference node, and the load neutral, which is this capital N. So there's no voltage drop across those 2 points, and that means what? If there's no potential between that, there's no current flowing in that conductor. So that's double star. No current flows. So even though 3 currents are dumped into that neutral, those 3 are in a balanced condition to where they sum to 0. Those non-zero 3-phase currents dump in, and because they are they're balanced, they're combined in a very special way to give you 0 current in the conductor. That's because of the way because they're balanced, the currents are all 120 degrees out of phase with each other, and they sum to 0. So no current flows in the neutral conductor. And that now gives us these 2 options that I was hinting at. We can remove the neutral conductor because the neutral conductor current is 0, or 2, we can replace the neutral conductor that we arbitrarily assign to have an impedance of Z0. We can actually replace that neutral conductor with a perfect short circuit. And that's because that potential, capital V sub capital N bar, is at the same potential as the reference node, little n. And that's what you've already seen then is actually happening. If we looked at the currents that are resulting, I sub AA is now this V sub A prime N minus V sub capital N over Z sub phi, which is just the source voltage, V sub A prime N, over the sum of those 3 impedances in the A phase. Likewise, I sub BB is V sub B prime N over Z phi, and I sub CC is V sub C prime N. Now, we know that the V's are balanced, and the Z phi is the same. We're dividing these particular oriented voltages by the same complex number. The I's are going to be all shifted by that 120 degrees. They're obviously going to be at a different phase than the voltage, unless Z sub phi is real. But if it's not real, it's the same in all three phases, and that allows our currents to all form a balanced three-phase set of currents. So if we find I sub AA, we know what I sub BB is automatically. It's just 120 degrees behind I sub AA. And I sub CC is 120 degrees behind I sub BB. Meaning, all we have to find is V sub A prime N, or know that, solve for I sub AA, and we have all the currents we need, all three-phase currents. These currents in each of the three lines so maybe I shouldn't say currents. Let me say current in each line is equal in amplitude and obviously frequency. We're still dealing with sinusoidal steady state. And those currents, phase-wise, are 120 degrees out of phase with each other. And because of that, that now allows us to analyze these balanced three-phase circuits in the YY configuration with just one single-phase equivalent. And that makes our job a little easier. Instead of having to re-sketch those YY configurations all the time, we can immediately draw or sketch a single phase of that circuit and analyze that. And that's our single-phase equivalent circuit. We now have a single-phase equivalent circuit that we can sketch. And that's going to look like V sub A prime N. There's the A prime. Here's the N. Here is our Z sub GA. There's A. Z sub LA. And that's now our single-phase equivalent circuit. Now, the only thing that you could possibly get in trouble doing is if you're analyzing this single phase, what you don't want to think about is that this is what's flowing in the neutral conductor. Remember, this is extracted out of a three-phase system. This current and the B and the C phase are all three in the true or in the actual neutral conductor. This is just a third of that current. You can find that current in this A phase and then determine the B phase and the C phase from this analysis. But if somebody says, oh, what's the neutral conductor? And you look at this circuit and you go, oh, it's carrying this current. Whoa, 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 whoa. It's carrying this, but it's also carrying B and C. So don't be jumping too far ahead in carrying what you're finding from this single phase equivalent into the full system. Is that clear? And that's why I said think of the neutral conductor as sort of three pieces, that you're pulling a third of it away and using that in your single phase equivalent. Here's the note that I want to try to make that point clear. I sub AA, that current, in the equivalent circuit is indeed equal to I sub AA in the balanced three-phase circuit. If you find I sub AA in this single-phase equivalent, that is the current that will be flowing in the A phase. What you can't jump and conclude is that the following. This I sub AA, where now I'm saying that's the current in the neutral conductor specifically, and maybe current in the neutral conductor in the equivalent circuit, that's not equal to the total current in the neutral conductor of the balanced three-phase circuit. Question? I'm sorry? Well, what we're doing here is what happens when we measure the voltage relative to the ground? In our analysis, or I'm sorry, the potential of little n with the ground, we're calling that our ground. That's our reference node. So we are not considering this to be floating anywhere else. We're just saying, well, I guess you could be, but we're not going to worry so much about grounding this system. In fact, what our analysis, we would then be tying that little n to our ground, and that's our 0 point. So we're not worrying about any potential difference between a ground and that little n. That was our reference node. That's our ground point, essentially, or effectively. This then says that if you need to find the current in the neutral conductor, if you've got a balanced system, it's 0. But just keep in mind that that is actually arising out of the combination, or the reason why it is 0 is because you're combining those three phase currents, and this is then the actual neutral conductor current. Questions on that? Yes? Yes, so if it's balanced, then once you've found I sub AA, you can immediately find I sub BB and I sub CC. You know if it's a positive phase sequence, you know exactly how the B and the C phases are related to the A phase. So once you've found the A phase, that's why you can analyze that single phase equivalent. Once you've found that, now you can find the other two. The B phase will be 120 degrees behind the A phase. If the A phase was something at 30 degrees, then the B phase is at minus 90. And the C phase is 120 degrees ahead of, or 100 of the A phase, or it's 120 behind the B phase. Is that making sense? So you don't have to separately find B and C. You can immediately compute those once you have the A phase. And that's the benefit of having a balanced three-phase circuit. You can immediately extract down the single phase, analyze the single phase, and now what do you want? You can tell us by finding that analyzing that single phase circuit. Question? Well, the amplitude is going to be the same. The question was, isn't the current going to be the same? The amplitudes at each of those currents will be the same, but the phases will be different because we know that those three currents have to sum vectorially to give us 0. I0 is 0 in a balanced three-phase system. I'm just making this equation because I want you to realize that if somebody says, oh, what's the current in the neutral conductor? And you've just analyzed it, so they're trying to throw you off. And they say, oh, you just analyzed the single-phase circuit. What's the current in the neutral conductor? And you look at your diagram and you go, oh, that's a mesh. That's the current in the neutral conductor. Just remember that you have two other phase currents to keep track of in the actual neutral conductor. Is that point made or understood? Let's now look at something that can maybe be a little more confusing, but all you have to do is go back to the basics and perform KVL. But now we want to talk about line-to-line voltages. And let's just concentrate for now on the positive phase sequence, the ABC sequence. And let's just look at it on the load side. On the load side, this is this configuration that I'm wanting us to use. And what we might find if somebody says, oh, what's the voltage in the A phase? What you would be finding in the single phase equivalent is you would be finding this potential difference between node capital A and node capital N. That would be the A phase voltage in this Y configuration of the load. That's what you would find in your single phase equivalent. Now what you may have is you may have a three-phase system and maybe somebody only has access to the line A or the node capital B. And they go, well, all I can measure is this polarity. Well, you're doing something silly. You're playing with a single phase equivalent and you're giving me this phase voltage. That's not a line voltage. It's a line to neutral voltage in the Y configuration, but it's not a line to line voltage. The line to line voltage is, in fact, this voltage. That's the difference. Now, where's the B phase voltage and how would it be labeled polarity-wise? It's between B and capital N. So we now have this phase voltage in the B phase. But once you found the A phase voltage, you can immediately write down the B phase voltage because you know it's a balanced set and you know it's just 120 degrees behind. Does everybody see that? And if somebody asks you for some other line voltage, maybe they give you the line voltage between line B and C. Or what's the other possibility? They could say, oh, actually, I'm interested in this line voltage between capital C node and capital A node. That's the C phase line voltage, or line to line voltage. And down here, this would be our V sub Cn, or our C phase voltage. I'm sorry? The phase shift between C and B, well, what is it? Our A phase here and B, so we're in a positive phase sequence, A, B, C. B is 120 behind A, C is 120 behind B. So C is 240 behind A, or 120 ahead of A. Just draw your diagram. I always draw a picture if you're kind of confused. So you have A, B, C. If you now tried to find the voltage between C and B, it's just the negative of the voltage between B and C. Right? You're just flip-flopping the polarity. So if you wanted to find the voltage with this, if you put your voltmeter positive lead at capital C and negative lead at capital B, that would be just the negative of flip-flopping the leads. Well, it depends on where you start. So if you found this V sub BC voltage, and you actually wanted to know the V sub CB voltage, you would simply have to negate that voltage, whatever the original ended up being. So now what I want to do is we've analyzed this single phase equivalent circuit. We can now find capital V sub capital A sub N. We can find that in our single phase equivalent. But that's maybe not what people have in the real world. Maybe they just have these terminals A, B, and C that they can measure. We want to know, what are you supposed to be measuring across A and B on the line-to-line voltage? We can do that by simply applying KVL. Since we know the A phase and the B phase from our analysis, we can find V sub AB. Let's write KCL, meaning what I'm wanting to do is simply write a KCL around that loop. I'm sorry, KVL. I want to do a KVL around that particular loop. KVL now says I have minus V sub AB plus V sub AN minus V sub BN equal to 0. Is everybody okay with that? I'm just finding my KVL, writing my KVL equation around that one section of my balanced three-phase circuit. What I want to do is find capital V sub capital A, capital B. And if I've analyzed my single-phase equivalent, I already can find the last two, V sub AN and V sub BN. Well, all we have to do now is some algebra. From this, I can say that V sub AB is simply V sub AN minus V sub BN. And you can do the same thing for finding V sub BC and V sub CA. To allow us to find capital V sub capital AB, let's just assume a given value for V sub AN. Let's say we've done our analysis and the result ends up giving us the following value for our A phase voltage. So this is what we're assuming we've just computed or calculated. It has a magnitude of V sub phi and it's a zero phase. If that's the case, what happens to our B phase? What does this equal? Knowing that it's a balanced three-phase set of voltages, what do we automatically know that we can write down? And this is a positive phase sequence. This is an ABC sequence. I can get the easy part. The amplitude's the same, right? V sub phi. Its angle, if you're walking around, it's minus 120 behind the A phase. And if somebody needed it, you could also supply them with V sub Cn. That's 120 behind B, or 120 ahead of A. What we want to do is use these two in here to solve for V sub AB in terms of what we've just computed in V sub phi. Yes? Is there like a restriction that keeps us from writing minus 240, or is it just like a... Okay, is there a restriction that forces us to not use minus 240? And the answer is no. It's just convention, that conventionally we keep our phase angle between 0 and 180 in value, between plus and minus 180. But no, there's nothing wrong with you saying V sub Cn is minus 240 as an angle. That's valid. That's correct. But typically we keep those numbers or values between 0 and 180 is all. Yes, between minus pi and pi. So if you're minus 240, you now add 360 to that, or you do something to give you the 120 that you want. Let's now find the answer that I'm trying to get you to, whoops, which is not that answer. What did I want? I wanted AB. And in terms of these phase voltages, that was V sub AN minus V sub BN. I hope that's the right formula. And the way that what we assumed those phase voltages were equal to, this was V sub phi at 0 minus V sub C at minus 120. Now we need to combine these vectors. And how do we convert or combine vectors? We typically put them into their rectangular pieces or components. We look at the horizontal piece and the vertical pieces, add those up, and then see what we have left, or see what results. In this case, we have an all-real piece because of that 0 angle, and the next one is now minus V sub phi. We take the cosine of minus 120, and then we say plus j, well, actually, it's this minus j, because of the minus sign, minus V sub phi sine of minus 120 degrees. Is that okay? What's the cosine of minus 120? Does anybody remember? It's minus 1/2. What's the sine of minus 120? So that's also negative, but it's minus the square root of 3 over 2. Let's now plug that in. We have a common magnitude. We have 1 minus a minus 1/2 minus a j minus square root of 3 over 2. Is that okay? So that we have v sub phi 1.5 plus j square root of 3 over 2. And now we should be able to sort of see what's going on. What's the square root of 3? 1.7 something. So we take half of that. That's about 0.85. We have 1.5 in the real direction and 0.85 in the vertical direction, roughly. That now gives us our length and angle. If we find the length of this vector, we square 1.5, we get 2 1/4. We square square root of 3 over 2 and we get 3/4. 2 1/4 plus 3/4 is 3. 2 1/4 plus 0.75 gives us 3, and we need to take the square root of that. So the magnitude of this number is the square root of 3, v sub phi, and what's the angle? We have the inverse tangent of square root of 3 over 2 over 1.5, which I think people are saying is 30 degrees. So what have we found? We found that if we ended up with the A phase voltage in our single phase equivalent, to get the line-to-line voltage, we would just have to increase the amplitude by this factor of square root of 3 and change its angle by 30 degrees, advance its angle by 30 degrees. And that will give us our A phase line-to-line voltage. Now that we know the A phase, and how did we get the A phase voltage? From our single phase equivalent. We analyzed that circuit. That was a fairly traditional analysis in sinusoidal steady state. Once we have that, now we can get the line-to-line voltage from this relationship. And once we have this, we can get V sub BC and V sub CA. They're all just 120 degrees behind the previous. They have the same amplitude. It's a square root of 3 larger than the A phase and the line in the A phase single phase equivalent circuit. And we'll have to pick up with the currents next time. But you should maybe what we should do, since I have 2 minutes, I can sketch in 2 minutes. What did we start with? Maybe this will make it a little cleaner. We started with V sub phi at 0 degrees. This was V sub AN. Yes? Then we had this guy. This was V sub BN. And this, that's supposed to be a straight line, is V sub CN. What do we know now about the line-to-line voltage? It's longer and 30 degrees advanced from where we started. So this is now V sub AB. Where's V sub BN? I'm sorry, V sub BC is down here, 120 degrees behind V sub AB, which if V sub BN was at minus 120, This one's now vertically down at minus 90. And the other one is again longer by what factor? Square root of 3, and it's ahead of that one by 30 degrees. Does everybody see how these phasors are related? Now graphically or pictorially versus in equations. We've now derived, if we now find this from this v sub phi at 0 in our single phase equivalent, we can now get the line-to-line information if somebody wants that. And we have the A phase current. What we now want to do is start talking about delta loads or sources and how to convert between deltas and y's. And once we can do that, we can solve all of these potential problems. We'll see you on Tuesday.